Yeah, so I'm Alexander and I'm co-founder at Fluence. And before coming to the decentralized world, I was working on some large-scale data processing. And well, I guess that's why the topic today is building a decentralized data processing infrastructure. Well, so to begin with, what's just a data processing? And a data processing, you can aggregate the data, sort the data, validate the data. And one would probably argue that making SQL queries is also some sort of data processing. And if you say, for example, look at the decentralized world, let's just check what kind of tools do we have there. And I know there are a hell of projects out there that do the data processing, but let's take just 3 of them, and namely Ethereum, IPFS/Swarm, or TrueBit. And let's just check out what do they provide us with. So first of all, there is Ethereum, and Ethereum is really secure, but it's, well, pretty expensive and quite slow, and probably not really suitable for the data processing except then trivial data volumes. And if I have lots of data, I might want to store this data somewhere. And that's what we can use IPFS or Swarm for. Basically what you can do, you can take your data and store it into some sort of decentralized network, and later on address this data using its hash. And it's already secure, it's decentralized, but there is like one problem with that. You or the client has actually to download the data. And what if I don't really want to load the data and process it myself? You can use, for example, TrueBit. And what does TrueBit do? It basically allows you to scale your computations by having special machines called solvers to perform the computation task. And then there are validators that are trying to challenge those solvers and basically find if the computation was processed incorrectly. And well, if there is some mistake made, then there is a dispute created, and this dispute can get escalated to Ethereum. And TrueBit can use Swarm as a data source, which is, well, really cool. But the problem with that is it's, well, mostly batch-oriented workload because you need to use Ethereum to create tasks. What if I want this data to be processed in the real time, right? So in lots of our lives, we have real-time use cases. For example, what if I'm trying to build a token wallet app? And for the token wallet app, the most common use case would be, well, there are rather trivial ones. For example, I want to be able to check the token balances, but I also might want to perform some more, I don't know, like advanced analytics. For example, I might want to, if I'm, for example, a miner, I might want to check how fast my mining rig performs against the entire network. So basically how many tokens my mining rig earns compared to the entire network, and I want to check this over, for example, the last year. And well, I might want to have some kind of mobile application, but I can't download the entire Ethereum on the mobile application. So now I'm like, all right, let's just query a full node. But I mean, I cannot really trust the intermediate full nodes, so I probably will have to query few of them. But there is another problem with that. Well, the full node might be slow, and honestly, they are not really super incentivized to perform advanced queries for me. So now, probably the next solution will be, well, to use some third-party server. And this third-party server will be, I can either set up it myself, or I can use some companies such as Infura, for example, to perform those computations. But that's not really decentralization, right? So you might ask me, what's the ideal vision? And I'll probably say, oh, something like that. And basically what you want to have a client, and there is a network, and you can ingest some data into this network, and the client queries this network, receives the results that are secure and fast and so on. And can we actually build that? Well, there are a few trade-offs, and I would probably say 3 of them that we probably need to take account for. So first of all, of course, like there is a decentralization part, but also you want to be able to process the data in the real time, and also you want to process it, cost efficiently. And when I'm saying real time here, I mean, I don't mean, the academic notion of the real time. It's not, hard deadlines or something. I mean more like marketing or industry sense real time. Well, if it's fast enough so the user doesn't really notice that. And cheap means, like, cost efficiency also means that it's at least like the same, price as Amazon would give you. So if you, for example, try to map the traditional cloud on that triangle, well, Amazon, for example, it will probably fit, it will be real time, and it will be cheap enough, but it's not really decentralized. If you try to map Ethereum there, it will be really secure, but not super real time, like 10, 20 seconds, and definitely not, not cheap enough. And TrueBit, which we have already discussed here, it will be secure enough, and it will be cheap enough, but not entirely real time. And the question is, can I achieve all of those three at the same time? Well, honestly, I'm not sure. Maybe one day ZK snarks and like zero knowledge and like stuff like that will come and save us all. But I'm not entirely sure. And here is the engineering approach. So that's what we are working on at Fluence. And basically, what do we have? We have a hybrid approach. And what we are trying to do, we are trying to provide the like somewhat secure results in the real time, and then have those results get validated thoroughly in the batch mode. And well, if the batch validation finds any mistakes that were made by the real-time nodes, then the client might get like a compensation. Or if you want some blood, well, you can find the real-time nodes with that. So roughly, this thing will look like this. You have a client, and you have real-time nodes, and the client only interacts with the real-time nodes. And there are batch nodes that are performing validation, and all of this system uses Ethereum, as a synchronization point. So the question is, can we build this using existing technology? How hard it will be? And let's just focus first on the real-time part. And for the real-time part, I think we can use small, efficient clusters for 4 nodes, maybe 7 nodes that are connected by the BFT consensus engine, such as Tendermint. And well, 4 or 7 nodes are not, entirely secure, but it's like good enough. In some cases, I think under certain assumptions, you might get 0.1% error rate or something lower, maybe. And those machines, the big aspect of them is that they have data locality. So the data is stored on the same machine that performs the computation, and this allegedly should help with the latencies when you're making your queries. And finally, there's machines that run WebAssembly, and you can, if you, for example, write your code, you can, in WebAssembly, you can submit it to those clusters, and they will run those computations for you. For the batch validation, the idea is that the real-time nodes, they have to store the history of the transactions they have made and the results somewhere, and then that batch validation will come and verify this later. And for this task, you can use Ethereum Swarm, and basically Swarm as a decentralized data storage will be used as a deep storage. Every time when the cluster receives a transaction, it stores it in Swarm, and the client, this moment, knows that once the client got the result, someone will come and verify this result, maybe a few hours later. And the way it's going to work with the batch validation. So batch validation is a bit different in the nature from the real time. And probably the first thing is that there is no data locality here. So because all of the transactions are stored in Swarm, any node in the network can become a batch validator. And now this batch validator, so first of all, because any node can become a batch validator, that allows you to have more security. So you know for sure those nodes are not going to form cartels with the real-time nodes, for example. And the way it works that batch validators, they walk through the history of operations. And once a new batch validator joins, it downloads the previous state snapshot, applies all of the transactions one by one to the state snapshot, if it finds any kind of mistake, well, it files a dispute, and if there were no mistakes, a new snapshot is produced and stored in Swarm, and the previous history, well, you can now delete that. So basically, you don't store the entire history from the beginning of the world, you just store the last few hours in Swarm. And probably we need to talk a little bit about the disputes. And so there are disputes that might happen, and those disputes might happen between real-time nodes, and they also might happen between real-time nodes and batch nodes, and between batch nodes themselves. So if basically what this means, if any node in the real-time cluster disagrees with what the fellow nodes have computed, it can file a dispute, and then you probably want to stop the real-time processing because the cluster is compromised anyways. But no matter how and when the disputes are created, they are getting resolved through the escalation to Ethereum. And well, the question is like, how do you escalate your computation to Ethereum? Because your computation is probably a really large one, and Ethereum cannot really process too much of the computations. Well, the way it works was proposed by Trubit, and if you guys are not really familiar with that, let me just say a few words. So imagine you have a function that sums two integers and returns this sum. And if you implement this function in the high-level language, it can get later on translated into the more lower, like assembly language. And here is an example from the from the WebAssembly. So basically what happens here, it reads the second input variable, pushes on the stack, reads the first input variable, pushes on the stack, and then the summation operation just reads first two elements of the stack and pops them and pushes back the result into the stack. So now if you have two nodes that have performed the computation, but one of them, well, we are trying to sum 3 and 5 here. So say, for example, one of those nodes have produced 8 and another has produced 6. How do you know which node is correct without repeating the entire computation? So what you can actually do, you can notice that the computation was mostly the same until the very last instruction. And you can now take this last instruction, send it to Ethereum smart contract, and send the stack state to the smart contract, and your smart contract might, well, tell you which result was correct and which result was wrong. And in overall, this entire architecture will probably look like this. Clients are talking to the Ethereum and talking to the real-time clusters, and batch validators can file disputes against the real-time processing part. And all of the transactions history is stored in Swarm. So that's basically an efficient real-time data processing platform, and I think it fits well with the rest of the decentralized stack, such as Ethereum, PFS, and Trubit. And now you might ask me what this thing might be used for. Oh, and by the way, that's how I would map it on this triangle trade-off. So it's not, I would probably say, an ideal solution. It's more of an engineering approach. You have real time, which is fast and like cost efficient enough, but is not 100% secure. It's somewhat secure. And you have the batch validation component that makes things a little bit more secure in the end, and also evicts bad actors from the network. So for the use cases, I would probably say there are at least some of them that can be decentralized databases or decentralized query layer infrastructure for blockchains, or maybe even decentralized stream processing or stateless web applications. And all the developer needs to do is to implement some WebAssembly code. Oh, well, I mean, if you don't really want to write WebAssembly, you can write C++ or Rust program or TypeScript, translate it to WebAssembly and deploy to the network, and then, say, for example, implement a decentralized website such as decentralized Etherscan, just which will be querying the network running this WebAssembly code. And well, again, that's what we are working on. And if you guys are curious, feel free to check out our GitHub. And if you like functional programming or Scala, well, you might be even more interested to check out that. And well, I guess thank you all, and Well, I guess we have questions if you guys want to. Mm-hmm.
First of all, thank you. First of all, cool choice with Scala. We're using as well a lot of Scala, so good choice. Correct me if I understand it wrong, but I still need to maintain my own Ethereum infrastructure and I need the data, right?
Yeah, I guess it kind of works. No, I mean, there will be a decentralized network for you.
But I mean, we're still getting data from Ethereum, and if you want some advanced data, you cannot use the Fura because you have to retrace the blocks if you need the bytecode. So you go for something like parity, and then you enable tracing, and you have to maintain the whole thing by yourself. So it does not help me with that. It's just something I need still to maintain my Ethereum infrastructure. Is it right?
Well, the goal was not to have you maintain your own Ethereum infrastructure. But let's maybe like discuss this after this talk. So maybe you can talk.
All right.
Tell a little bit
All right.
about use case.
Cool. Thank you. Thank you, Dan.
Hi. Who will pay and for what?
Thanks. Well, the question was who gonna pay and for what? So the incentivization model still has to be figured out. But the idea is that either the clients that are making queries will pay, and they will probably pay for the amount of the computation performed and the amount of data stored over time. Or if you, for example, when you just deploy a normal website, you have a developer who deploys the website and pays for the hardware. So we might have a developer of your smart contract, which is in WebAssembly, to pay for that, and the clients might just access it without any fees. And all of the money will go to the miners who run the network.
Okay, thanks.
What are the limitations of computations which could be performed?
So right now we are having very specific limitations coming from the WebAssembly. So WebAssembly memory is under 4 gigabytes. So if your data cannot fit into 4 gigabytes, you will probably have to shard that. And we haven't really figured the sharding aspect yet. Well, I mean, you can always do the hash-based sharding, but more advanced. Like, I mean, I don't think you will be, at least right now, we'll be able to perform the joins, for example. If you are building really large-scale tables, you probably won't be able to perform joins, because distributing data when you perform joins, even in the normal data center, is pretty hard. But in the decentralized infrastructure, it's probably impossible. But streaming joins, well, maybe, I guess. And yeah.
Can I query external sources like web APIs and so on?
The problem with that is that for the disputes, for the verification game, you want basically you want predictability, right? Like you want repeatable computations. You want I forgot the word honestly, but anyways. If you, for example, query an external API and one day it will return you one thing and tomorrow it returns other stuff, then probably it's not going to work. But the data such as Ethereum, for example, or if you forget about, finality stuff, or data stored in Swarm or IPFS, it can definitely be queried. And I think we're gonna just develop different, plugins. We will allow to plug different data sources into the system.
Where the state of computations is stored?
It's stored on the real-time nodes. The state of the computations is stored on the real-time nodes. So basically, all of the idea is that you have data local computations. So for example, let's imagine, let's imagine a B-tree traversal. So when you perform a B-tree traversal, you need to, from the root to the leaf, you have to basically fetch 4 buckets, for example. And if those buckets are stored somewhere outside of your nodes, well, this will increase your latency. But if all of those buckets, or most of them, are stored on your local machine and cached in memory, then you can perform much faster search. And that's the idea, that the data is stored at the same machine where the computations are performed.
Last question. What do you think, and how you think user experience could look like in a case then real-time solution was proved wrong. For example, user saw a balance of $1,000 in his wallet, and then later batch nodes say to him, sorry dude, it was a mistake, actually you have zero.
Right. Well, great question. Well, I mean, I don't think you are going to use that for, to send someone $1 million. It will probably be something that, well, if it goes wrong, you probably are not going to lose much. If, for example, your token wallet balance was shown to you incorrectly, and you don't use it to make, large-scale investment decisions, then you're probably fine. You will either get compensated, or at least those nodes gonna get fined. Well, anyways, your wallet will eventually get updated with the correct ones. So the way it works, I think I can envision that. Basically, you can either roll back the entire history of transactions until the point where the incorrect one was made, or you will try to fix an error by the batch computation.
Thank you.
I think there was another question right there.
Hi, thanks for the presentation. So what Rubit tries to solve is verifying computation without re-executing it, without too much replication attached to it, and they have an incentive game which is basically some kind of panopticon, and you can introduce false errors into that, and that makes the system stabilize. What they're suffering from mostly is data availability for external verifier to enter and to make sure that he has the same inputs. So I'm trying to figure out here what's your vision. Like you're saying that, well, we're gonna spin up multiple Trubit nodes in order to have a bit of redundancy in the processing, and those will also be the verifiers or the challengers. And secondly, you're saying that you're solving the availability problem by attaching to a network with high availability like Swarm or something else. Is that correct?
Yeah, correct.
Okay, then I get it. Well done.
Thank you for the presentation. I really like it. So I have two questions. So first question is, in terms of numbers, could you give any numbers for the benchmark? Did you do anything?
Well, that's very highly the work in progress right now. So I can't make those promises yet.
Okay. And maybe the second one is like functional programming. I'm just curious, how does functional programming help you to build this database?
Could you say the question once again, please?
And in terms of like functional programming, how does it help you to build a database? Like, what concepts are you using to build this?
Oh, well, we are using Scala, and we are using basically what we are trying to do, we are trying to isolate side effects with monads, such as IO monad. And basically, we also have concurrent computations, and we also, when your side effects are isolated, then, and your functional programming helps you with this, you basically can reason much better about concurrency. And
okay, thanks.
Cool, I guess that's all.
Yeah, thank you, Alexander.
Thanks, guys.